Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell somewhere down there, and you'll get notifications for this series and a bunch of other ones on our channel. We do math, all kinds of math. Right now we're doing multivariable calculus. We're in chapter 2, which is double and triple integrals. In particular, 2.6 is triple integrals now, and this lecture we're going to do finally. Last lecture we did the derivation of how to do the 6 kinds of phrasing general solids E. Now what we're going to do is do some of those integrals examples, triple integrals, and then we'll start doing applications, which is going to be, the first one will be volumes using triple integrals. Let's do that. Example 1, we're going to compute the triple integral over E of x dv, where E is the solid in R3 bounded by the paraboloid x equals 4y squared plus 4z squared, and the plane x equals 4. What? Exactly. Right, Kitty? So what we're going to do first is we're going to draw these regions. On exams, a lot of the time, what I like to do, or if they're reasonably nice because you don't have very much time, is hopefully the picture's also in the question so you don't have to set it up. Either way, that's not giving everything for free, because even once we have the picture and that's correct, then you have 6 ways of phrasing that. So you have to choose which one and then compute the integral that way. So first of all, what we're going to get is it's going to intersect at a circle. This plane is going to cut this way in the x direction. X is going to be a vertical plane this way. And it's going to intersect this thing. This is a paraboloid, so this is circles. If you factor out the 4, this is 4 times x or y squared plus z squared. So you're going to get bigger and bigger circles if you look at the level surfaces, level curves of these guys. And so what that's going to give me is this guy that goes to the origin. What that's now going to give me is that fixes my x and y axis. This is going to be z, and this will be y, and then this is going to be the x axis. This is x equals 4, and this is x equals 4y squared plus z squared. Also, even if I couldn't draw it, we're drawing it because we're doing the video, so this is the whole point. We want fancy pictures so that you can see, oh, there's a paraboloid. And then what's going to happen? Once I fix that, what I'm going to do is phrase that as what? It doesn't matter that you memorized what type they are. Luckily, they gave it to us in the problem. X equals and x equals. That probably means I'm going to phrase x as a function of y and z. I just have to, the picture helps me see that now. What is that going to go from? X goes from the paraboloid up to the plane 4. So what that says is I have a type 2 solid E that I'm going to phrase it as. And in that means that in my bound specifically, I have 4y squared plus z squared is less than or equal to x is less than or equal to 4. Those are my 2 functions of y and z. That's what makes it a type 2 solid E. You don't have to memorize what type it is. There's 3 types. Type 1 supernova, type 1a supernova, and type 2 supernova is what? Type 1a has hydrogen or doesn't have hydrogen. I don't remember. The names are arbitrary, but either it does or it doesn't. You don't have to memorize that, but you have to figure out whether hydrogen is present or not. Here, I have solid type 2, and then what am I going to do? Now that I fix that, I project that onto the YZ plane, and I'm going to get this circle in the YZ plane, but which circle? In the YZ plane now, we're going to get which circle? This says when 4 is equal to 4y squared plus z squared, we get y squared plus z squared equals 1. So this is the region y squared plus z squared is less than or equal to 1. And what that means is I'm probably going to want to switch and use polar coordinates. So therefore what I'm going to do instead is phrase that as 0 is less than or equal to r is less than or equal to 1, and 0 is less than or equal to theta is less than or equal to 2 pi. This is going to be my bounds for my region D, which is now polar region, not type 1 or type 2. I phrase it as polar. Now that I have type 2 solid E and polar region, I have my bounds. I can phrase this triple integral, and then we'll erase and compute. This picture is stage 1 and stage 2. First, draw it accurately. Hopefully, if they're nice, they give it to you, or you can use GeoGebra or some other kind of Desmos to draw. Then once you have that, you have to still phrase what type your solid is, then project into which plane you're in. This was the YZ plane, which is the projection of that onto there, so what we're bounded over. Now what we're cleverly going to say is this triple integral over e of x dv is equal to the double integral over our region D of the integral from 4y squared plus z squared to 4 of x dx dA. And that's cleverly phrasing that. There's the trick that you're going to steal now. Why have I done that in 2 stages? Because if I kept it in rectilinear or Cartesian like I normally would have, then I could have put the other 2 bounds and then phrased these bounds. But these bounds would be horrible because it would be y goes from -1 is less than or equal to y is less than or equal to 1, and then z is going to go from negative the square root of 1 minus y squared is less than or equal to z is less than or equal to the square root of 1 minus y squared. So those are horrible rectilinear bounds, and then I could just put them in there. Instead, what I'm going to do is just keep it as the region D and rephrase and put it in polar in a second after I compute this antiderivative. Why not? So equals the double integral over D of this I can compute. This is 1/2 x squared evaluated from 4y squared plus z squared to 4 dA. Now let's move it up and compute the rest of this. Moving that up and using the fundamental theorem of calculus, I put the bounds in. I get 4 squared minus 4 squared times x squared plus y squared, which is going to give me, what am I going to get? I can pull the 16 out. 16 over 2 is 8. I'm going to get 8 times the double integral over the region D that we had. Remember, what's our region D? It's the unit circle or the unit disk. And that's going to give me 1 minus y squared plus z squared dA. And this is where I see I have y squared plus z squared is less than or equal to 1, and I have y squared plus z squared. So now what we're doing is polar, but it's in the y, z region. So that says y is r cos theta, and z is r sine theta, and y squared plus z squared is equal to r squared. That's going to make that a whole lot easier to phrase is what I'm saying now. This is now equal to 8 times the double integral over d of 1 minus r squared, and then what was our region? That was 0 to 2 pi, 0 to 1 of r dr d theta. That now gives me equals 8 times the integral from 0 to 2 pi d theta times the integral from 0 to 1. I get r squared. Distributing that in, I get r minus r to the 5 dr, which is going to give me what? This is going to give me here, I'm just going to get 16 pi times 1/2 r squared minus 1/6 r to the 6 from 0 to 1, which is going to give me 16 pi times 1/2 minus 1/6, which is 16 pi times 3 minus 1, which is 2 over 6, which is 1/3, or 16 pi over 3 is the hypervolume to the power 4. Next, example 2, we're going to compute the triple integral of z over this region E, where E is the solid bounded by a cylinder y squared plus z squared equals 9, and the planes x equals 0, z equals 0, and y equals 3x in octant 1. Now we have 8 octants instead of 4 quadrants, and we want it in the first octant. What is that going to look like? It wants x equals 0 is this plane. Z equals 0 is the xy plane, this one. Y equals 3x, this is the xy plane, and it's going to cut like this, and so that's what you're going to get in the plane. We're going to project down on that, so that's this guy from here to here. That's this plane, and it's going to vertically come up like this. How do we make it look like that? First of all, it says it's bounded by this one also, so from here to here, I'm going to get the curvy part of the paraboloid now. You'll see it's not straight, and then we're going to get also, it's going to come down onto that, and that is going to be the surface that we actually have. What are those? Hopefully you can see that that's what the object is, that wedge. This is, I'm going to phrase as the way that I want to. This is z equals the square root. I'm solving for z. This is the square root of 9 minus y squared. This is the plane y equals 3x. Again, that's what I'm saying. I'll try to be nice and give you those in my classes at least. Now that you have that, you have to phrase that as what are we doing with this? I'm seeing that I'm phrasing z. Z is going to go from 0 to this guy. So I can phrase it as a type 1 region E, which I like to do. So that's going to give me type 1, and therefore I'm going to project down onto the xy plane. And that will, in the xy plane, what is that going to give me? X is 1 and y is 1, 2, 3, and we're going to get that triangle in this plane, which is going to be this one. This is our region D. Now, what do we have? This is y equals 3x, and this is y equals 3. So what we can do is phrase that as what that's going to be is 0 is less than or equal to x is less than or equal to 1, and 3x is less than or equal to y is less than or equal to 3. So again, we have a type 1 region D, just the way that I want it. And where does z go from? 0 is less than or equal to z is less than or equal to the square root of 9 minus y squared. Now we have our bounds. Now we can compute the triple integral. Doing that, we have the triple integral over e of z dv is now equal to the integral from 0 to 1, the integral from 3x to 3, the integral from 0 to the square root of 9 minus y squared, z dz dy dx. There's the setup. Now what we have is this is equal to the integral from 0 to 1, the integral from 3x to 3 of 1/2 z squared evaluated from 0 to this, which is just going to give me 9 minus y squared dy dx. Real estate's at a premium on the board, so I didn't want to write the stuff in there, but I used the Fundamental Theorem of Calculus Part 2 to put that in there. Tattoo it on yourself, you'll have it reminded, and then you do that in your head. I cheated, I tattooed it. So there. Now what do? I'm going to evaluate that at y and hold x constant. This is going to equal the integral from 0 to 1 of 1/2 9y minus 1/3 y cubed evaluated from 3x to 3 dx. Putting that in there, and I don't need this anymore because I have my bounds. This is equal to the integral from 0 to 1 of 1/2, and now I'm going to get 27 minus 9 minus 1/2. Putting this in here, I'm going to get 27x minus 1 over 3 times 27x cubed dx, which is going to equal 1/2 the integral from 0 to 1 of 18 minus 27x minus 9x cubed, if I did that right, dx. Now let's move that up and compute finally. Okay, moving that up, we get the antiderivative again using the Fundamental Theorem of Calculus Part 2. Sorry, this should be a plus. Get it right. And then now this is the correct antiderivative. Computing this, I want to put the 1/2 in there to simplify a little bit before I do that. So doing that, I'm going to get 9x minus 27 over 4x squared plus 9 over 8 evaluated from 0 to 1, which now gives me 9 minus 27 over 4 plus 9 over 8. I need a common denominator. 8 is the common denominator, so I need, this is equal to 72 over 8 minus 54 over 8 plus 9 over 8, which is 72 minus 54 plus 9 is 27 over 8. Let's do one more. Example 3 says, use the triple integral of 1 dv to compute the volume of a solid E bounded by the coordinate planes x equals 0, y equals 0, z equals 0. The plane z equals 2 minus y, and the cylindrical surface x equals 4 minus y squared. We'll draw that in a second. But first of all, we had a property of double integrals. If I want the area of an arbitrary region D in the plane, and I can phrase that as a type 1 or a type 2 or a polar region, I can compute that as the double integral D of dA. That gives me the area of D. Similarly, now what we're saying is if I want the volume of an arbitrary solid E, that is going to be simply the triple integral of 1 over that region dV. This is going to give me a volume of E, is what we're talking about in that scenario. And that's the machinery we're going to use. So we have to phrase our solid E, draw the picture of it, and then once we have that, we have our bounds, and we can compute that, and we don't have any integrand. We just compute the integrand of 1, which will be nicer to do that. Get one of these in there. Oh, hinges. Your knuckles. Get in there straight. I want it that way. Example 3 now, specifically for our solid. You don't need to see me generate that, or if they're nice, they give it to you. There it is. Now you have to pick. What I'm going to do is, also I wanted to show in these videos to phrase it slightly differently, and I always try to default type 1 if you can, so do that. But I'm going to, if we do type 1, it would go from z equals 0 to z equals 2 minus y. And then in the xy plane, we're going to get the parabola. If you can see it in the xy plane, we'll get the parabola that opens downwards from 4. Actually, no, it's going to do that from 4, x equals 4 down to y. Oh, it's x equals y squared. And that's what you get in the region in the xy plane. You can try that one if you want to phrase it as type 1. I'm going to phrase it as type 2. What does that mean for us? Phrasing it as a type 2 region, that means that x is going to go from 0 to 4 minus y squared. Now I have my bounds of my region, and this is the best kind because we're just finding the volume of this object. It's going to be a fraction, which is strange. There's no pi's or anything in there. Well, what is the exact volume? Let's find out. The volume of this region E now is equal to the triple integral over that region of 1. And that's going to be phrased the way that we did it. That's going to be the integral from 0 to 2, the integral from 0 to 2 minus y, the integral from 0 to 4 minus y squared, dx, dz, dy. This is how we phrased this object. Once I do that, I iterate immediately. Doing dx, there is nothing there, so I'm going to get just an x evaluated from 0 to 4y squared, which is that thing. So that's going to be equal to the integral from 0 to the integral from 0 to 2 minus y of 4 minus y squared minus 0, dz, dy. I do the same thing. I take the antiderivative of z. There's no z's there, so I get 1z evaluated from 0 to 2 minus y. That will give me the integral from 0 to 2 of 4 minus y squared times 2 minus y minus 0 dy. Foil everything out. I'm going to get the integral from 0 to 2 of 8 minus 4y minus 2y squared plus y cubed dy, which is equal to 8y minus 2y squared minus 2 over 3y cubed plus 1 over 4y to the 4th, evaluated from 0 to 2, which is equal to 16 minus 4 times 2 is 8 minus, where are we going to get 16 over 3 plus 16 over 4, which is 4. So we're going to get 12 minus 16 over 4, which is multiplying by 4 over 4 is 36 minus 16 over, sorry, that should have been it. What are you doing? I even said 4 and my brain was doing the right thing, even my mouth wasn't. It's over 3, so multiplying 12 by 3 over 3 will give you 36 over minus 16 is equal to 20 over 3. Math is hard, keep trying. Please subscribe right here and hit the notification bell. You'll get notifications for this and other series on our channel. Basically what we're going to do next time is we are going to do more of these applications, starting with volumes again, and then we will do the same thing, but we want to know what is the electrical charge on this. If it has a charge density varying over this object, we can use triple integrals to find center of mass and a charge density and moments of mass and moments of inertia and all of those fun things. We're going to do that next time. See you then.